Right now, 25 trillion miles away, there is a planet that might harbour life. Proxima b orbits in the habitable zone of our nearest stellar neighbour. Scientists have confirmed its existence. We know its mass, its orbit, its potential for liquid water. For the first time in human history, we have a target. A world close enough that reaching it seems merely difficult rather than impossible. Except it is impossible. Not because of distance, not because of time, not because we lack clever engineering or sufficient ambition. One equation written over a century ago by a Russian mathematician explains why no human will ever walk on Proxima b. The Tsiolkovsky rocket equation is a wall that no technology can break. If you want to understand why the stars will forever remain out of reach, hit that like button and subscribe. Now, get yourself comfortable. Let's begin. .24 light years. Write that number down. Memorize it. Let it sink into your understanding of what humanity faces when we dream of reaching other stars. This distance represents everything our species has ever imagined about escaping the cosmic loneliness of our solar system. Proxima Centauri, a dim red dwarf star, floats through the galaxy at precisely this separation from our Sun. It is the closest star to Earth besides our own. Orbiting that faint stellar ember is a world that changed everything we thought we knew about our place in the universe. Scientists discovered Proxima b in 2016 after years of painstaking observation. They detected it not by seeing it directly, but by measuring the subtle wobble it induced in its parent star. Every time the planet completed an orbit, it tugged Proxima Centauri slightly off-center. That gravitational signature revealed a world roughly 1.3 times the mass of Earth, orbiting in a zone where liquid water could potentially exist on its surface. For the first time in human history, we had a concrete destination outside our solar system. Not a theoretical target, not a mathematical abstraction, a real world that might harbour oceans, atmospheres, and perhaps even life. The discovery electrified the scientific community and captured imaginations across the planet. Here was proof that rocky worlds orbit other stars at distances hospitable to biology. Here was a target close enough that reaching it seemed merely a matter of engineering rather than fantasy. Space agencies began studying mission concepts with renewed urgency. Billionaires funded research initiatives aimed at interstellar probes. The dream of sending something, anything, to another star system suddenly felt tangible in ways it never had before. But dreams shatter against mathematics. The distance to Proxima b conceals a truth so devastating that most space enthusiasts refuse to accept it, even when confronted with the calculations. We will explore that truth in exhaustive detail over the course of this journey. By the end, you will understand with absolute clarity why no human being will ever set foot on that distant world. The reason is not technological immaturity. It is not lack of funding or political will or imagination. The reason is a fundamental law of physics that no amount of cleverness, no breakthrough in engineering, no revolutionary discovery can ever circumvent. First, we must grasp what 4.24 light-years actually means in terms human minds can process. The number sounds deceptively small. 4 is a number we encounter constantly in everyday life. 4 seasons, 4 directions, 4 wheels on a car. The smallness of the number tricks our intuition into believing the distance is manageable. It is not. Light travels at approximately 300,000 kilometers per second. This is the cosmic speed limit. Nothing in the universe moves faster. No particle, no wave, no information of any kind can exceed this velocity. A beam of light leaving Earth right now would reach the Moon in 1.3 seconds. That same beam would arrive at Mars in roughly 3 minutes when the planets align favourably. Light crosses our entire solar system from the Sun to Neptune's orbit in approximately 4 hours. Now keep that beam travelling. day after day, week after week, month after month. The photons race through the void at speeds that make our fastest rockets look stationary by comparison. After an entire year of constant travel at the absolute maximum velocity physics permits, that beam of light has covered 1 light year. Approximately 9.5 trillion kilometers, almost 6 trillion miles. Proxima b lies 4.24 times that distance away. The light you see from Proxima Centauri tonight, that faint reddish pinprick visible only through binoculars in the southern hemisphere, left that star over 4 years ago. When those photons began their journey toward your eyes, you were living a different life. Whatever happened to you 4 years ago, whatever joy or sorrow or ordinary Tuesday you experienced, was still in your future from the perspective of that ancient starlight. The universe you observe when you look at Proxima Centauri is not the universe as it exists now. It is the universe as it existed before the last presidential election, before the last World Cup, before countless human births and deaths. Converting this distance to kilometers yields a number that loses all practical meaning. 40 trillion kilometers. Written out, that becomes 40 followed by 12 zeros. 40 million kilometers. But abstract numbers fail to communicate scale. Our brains evolved to understand distances we could walk, distances we could throw a spear, distances between water sources and hunting grounds. We have no intuitive grasp of trillions. Let me try a different approach that might help anchor this cosmic gulf in something resembling human experience. Imagine shrinking the sun to the size of a basketball. At this scale, Earth becomes a small pebble roughly 2 millimeters across, orbiting 26 meters away from our basketball sun. Jupiter, the giant of our solar system, sits 130 meters distant as a marble about the size of a large grape. Neptune floats 750 meters from our basketball sun, nearly half a mile away. The entire solar system from the sun to the edge of the Kuiper Belt. Everything humanity has ever directly explored with spacecraft spans roughly 3 kilometers at this scale. Now, where would Proxima Centauri sit in this scaled model? 6,800 kilometers away, the distance from New York City to Rome. Our entire solar system, compressed into a 3-kilometer neighborhood, becomes a single house on a street that stretches across the Atlantic Ocean. Every probe we have ever launched, every planet we have ever photographed up close, every asteroid and comet and moon we have mapped, fits within a modest walk. The nearest star floats on another continent. This scale model begins revealing the true horror of interstellar distances. But the horror deepens considerably when we consider how fast our spacecraft actually travel. Voyager 1 holds the record as the fastest object humanity has ever launched relative to the Sun. This remarkable spacecraft left Earth in 1977, the same year the first Star Wars film premiered in theaters. It has been accelerating through gravitational assists and coasting through the outer solar system ever since. Currently, Voyager 1 travels at approximately 17 kilometers per second, 61,000 kilometers per hour, roughly 38,000 miles per hour. This velocity exceeds anything humans have achieved with any other spacecraft by a significant margin. At this blistering speed, how long would Voyager 1 need to reach Proxima b? 73,000 years. Let that number sink in. 73 millennia. If our ancestors had launched Voyager 1 when they first developed cave paintings, when they hunted mammoths across Ice Age plains, when the very concept of agriculture lay 30,000 years in the future, that spacecraft still would not have arrived at our nearest stellar neighbor. Human civilization would need to persist for nearly 400 generations, through climate shifts and ice ages and continental drift, merely for our fastest spacecraft to complete this journey. Clearly, Voyager speeds will not suffice. We need to go much, much faster, and here is where the nightmare begins in earnest. In 1903, while the Wright brothers were preparing for their historic flight at Kitty Hawk, a Russian schoolteacher named Konstantin Tsiolkovsky was working on calculations that would define the ultimate limits of space travel forever. Tsiolkovsky derived an equation so fundamental that every rocket ever built, from primitive fireworks to Saturn V moonshots to theoretical antimatter drives, must obey its constraints. This equation appears simple when written on paper. Its implications are catastrophic for human ambitions in space. The Tsiolkovsky rocket equation states that the change in velocity a spacecraft can achieve depends on two factors: the exhaust velocity of its propellant and the ratio between the spacecraft's initial mass and final mass. In mathematical notation, delta V equals exhaust velocity times the natural logarithm of initial mass divided by final mass. Let me translate this mathematical statement into plain language that reveals its terrible meaning. When a rocket engine fires, it throws exhaust gases out the back at tremendous speed. Hot combustion products, ionized particles, or whatever propellant the engine uses, exit the nozzle as fast as physics and chemistry allow. By Newton's third law, every action has an equal and opposite reaction. The force pushing those exhaust gases backward creates an equal force pushing the rocket forward. This is how all rockets work, from bottle rockets to interplanetary probes. The faster you can throw that exhaust, the more efficiently you accelerate your spacecraft. That is the exhaust velocity term in the equation. But here is the critical insight that destroys interstellar dreams. Every kilogram of fuel you carry must itself be accelerated, along with everything else. The fuel is not free, it has mass, and that mass requires additional fuel to accelerate. The fuel to carry the fuel requires more fuel still. The fuel to carry the fuel adds yet more mass. This creates an exponential relationship between the speed you want to achieve and the mass of fuel you need to carry. Exponential relationships sound abstract until you see them in action. Let me show you what happens when we calculate fuel requirements for interstellar velocities. Chemical rockets like the engines that took humanity to the moon achieve exhaust velocities around 4.5 kilometers per second. This represents the maximum energy that chemical bonds can release when fuel combines with oxidizer. Hydrogen burning with oxygen, the most energetic chemical reaction practical for rockets, cannot push exhaust gases faster than this fundamental limit. To reach just 1% of light speed using chemical propulsion, the mass ratio required becomes e raised to the power of 667. If you are unfamiliar with exponential notation, let me make this concrete. This number exceeds the estimated number of atoms in the observable universe. Not atoms on Earth, not atoms in the solar system, not atoms in the Milky Way galaxy, atoms in every galaxy in every direction, out to the cosmic horizon, 14 billion light-years away. You would need more fuel than exists in all the matter you can see in the night sky. Perhaps you think 1% of light speed sounds excessive for a first attempt. Let us be far more modest in our ambitions. Voyager 1 travels at 17 kilometers per second. What if we wanted to reach just 100 kilometers per second, roughly 6 times faster than our fastest spacecraft? This seems like a reasonable next step, a significant improvement without venturing into percentages of light speed. Even this humble velocity improvement requires chemical rockets to carry billions of times more fuel than payload. The mathematics are unforgiving. A spacecraft weighing 1,000 kilograms at arrival would need to launch with fuel mass exceeding anything humanity could construct or even imagine constructing. And 100 kilometers per second still requires roughly 13,000 years to reach Proxima b, longer than recorded human history, longer than the time since the last ice age ended. And this is the scenario requiring fuel masses that already exceed comprehension. The exponential nature of the rocket equation means that small increases in desired velocity require enormous increases in fuel mass. This is not a linear relationship where twice the speed needs twice the fuel. The mathematics are far more punishing than linear scaling. Every additional unit of velocity demands proportionally more fuel than the previous unit. The curve rises ever steeper as velocity increases. Visualize this exponential growth with a simple thought experiment. Imagine you have a cup of coffee on your desk. Doubling the amount of coffee in that cup seems trivial. You pour another cup. Now you have 2 cups. Doubling again gives you 4 cups. Keep doubling. 8 cups. 16. 32. 64. After just 10 doublings, you have over 1,000 cups of coffee. After 20 doublings, you have over 1 million cups. After 30 doublings, you have over 1 billion cups of coffee. Your desk is buried. Your house is buried. Your neighborhood drowns in coffee. This is exponential growth in action. The rocket equation operates on the same principle, but the numbers actually grow even faster because the natural exponential function underlying the equation rises more steeply than simple doubling. Fuel requirements do not merely double with each increment of velocity. They follow a curve that accelerates upward with increasing ferocity. This mathematical reality creates what engineers call the tyranny of the rocket equation. No matter how much fuel you add, the returns diminish with crushing finality. Each additional kilogram of fuel provides less velocity benefit than the previous kilogram, because each additional kilogram must also be accelerated. At some point, adding more fuel actually slows your acceleration because the additional mass outweighs the thrust benefit. You hit a wall that no amount of additional propellant can breach. For interstellar distances at speeds that matter, that wall appears almost immediately. Consider what fraction of light speed we actually need to reach Proxima b within a human lifetime. If we wanted to arrive in 50 years, a single long career's worth of waiting for results, we would need to average roughly 8.5% of light speed. That works out to approximately 25,000 kilometers per second. This velocity is so far beyond anything humanity has ever built or seriously designed that it barely registers as engineering. It lives in the realm of physics thought experiments. Using chemical rockets, the mass ratio for this speed requires numbers so large they transcend meaninglessness into absurdity. If you wanted to send a 1 kilogram payload to Proxima b at this speed using chemical propulsion, you would need more kilograms of fuel than there are atoms in the Milky Way galaxy. Not stars, atoms. Every proton, neutron, and electron in 400 billion stellar systems would not provide enough matter to fuel this journey. This is not an exaggeration for dramatic effect. This is not hyperbole to make a point. This is the actual mathematics that follow directly from the Tsiolkovsky rocket equation applied to the velocities and propulsion systems we are discussing. The equation does not care about human dreams. It does not respond to ambition or funding or determination. It describes a physical law as immutable as gravity or the conservation of energy. Perhaps you are thinking that chemical rockets represent old technology. The Saturn V flew over 50 years ago. Surely nuclear propulsion or ion drives or some advanced engine concept developed since then can defeat this tyranny. Surely human ingenuity can find a way around an equation derived by a schoolteacher in Tsarist Russia. This hope brings us back to the fundamental structure of the rocket equation itself. The only way to improve mass ratios within the equation is to increase exhaust velocity. If you can throw your propellant out the back faster, you need less of it to achieve the same change in velocity. This relationship is mathematically certain. It emerges directly from conservation of momentum, one of the most fundamental principles in physics. Every propulsion technology ever conceived must operate within this framework, if it carries its own fuel. Chemical rockets max out around 4.5 kilometers per second exhaust velocity, because that number represents the maximum energy that chemical bonds between atoms can release. When hydrogen and oxygen combine in a rocket combustion chamber, the heat generated accelerates the exhaust products to this velocity. No chemical fuel combination can significantly exceed this limit, because no chemical bonds store significantly more energy. Chemistry itself imposes this ceiling. Nuclear propulsion increases exhaust velocity by using atomic rather than chemical energy. Ion drives increase exhaust velocity by accelerating particles electromagnetically. Plasma engines increase exhaust velocity through various electromagnetic confinement schemes. Each technology pushes the exhaust velocity number higher than chemical rockets can achieve. But the exponential function of the rocket equation remains in force regardless of what technology generates the exhaust. Even with dramatically improved exhaust velocities, the tyranny of mass ratios waits patiently at higher velocities. Increasing exhaust velocity does not eliminate the exponential wall. It simply moves that wall farther away. The wall still exists. You will still hit it eventually. Let me demonstrate this truth with nuclear thermal propulsion, one of the most promising near-term advanced propulsion concepts that engineers have actually built and tested. Nuclear thermal rockets heat hydrogen propellant using a fission reactor core. Instead of burning the hydrogen chemically, the nuclear reaction provides heat that expands the hydrogen and accelerates it through a nozzle. This approach achieves exhaust velocities around 9 kilometers per second. NASA tested these engines extensively during the 1960s and 70s under a program called NERVA. They worked. The technology is real. To reach 8.5% of light speed using nuclear thermal propulsion instead of chemical rockets, the required mass ratio drops from impossible to merely impossible. The exponent in the mass ratio calculation falls significantly, but the resulting number remains incomprehensibly large, still utterly beyond any conceivable fuel supply. Doubling exhaust velocity barely dents the problem at interstellar velocities. Every advanced propulsion concept ever proposed faces this same exponential wall. Nuclear pulse propulsion, where nuclear bombs detonate behind a spacecraft and push against a shock absorber plate, achieves higher exhaust velocities. The wall moves back. Fusion propulsion, harnessing the energy source of stars, achieves higher exhaust velocities still. The wall moves back further. Theoretical antimatter propulsion, annihilating matter with antimatter for the ultimate energy release, achieves exhaust velocities approaching meaningful fractions of light speed. The wall moves back yet again, but the wall never disappears. The exponential function governing mass ratios continues to climb toward impossible numbers at sufficiently high velocities. The wall can be pushed back. It cannot be broken. This is not a limitation of current technology. It is a fundamental property of how momentum conservation works in a universe where spacecraft must carry their own propellant. This brings us back to the real wall we face, the wall that makes human interstellar travel impossible. The Tsiolkovsky rocket equation is not a technological challenge awaiting a clever engineering solution. It is not a puzzle that sufficiently smart people will eventually solve. It is a mathematical relationship that describes physical reality. That relationship says the following with absolute certainty. If your spacecraft must carry the energy source that propels it, exponential mass growth applies. And exponential mass growth means that interstellar velocities require fuel masses that exceed not just planetary scales, not just stellar scales, but galactic scales. The only way to escape this tyranny entirely is to not carry your propellant at all. External propulsion systems like laser sails attempt this radical approach. A spacecraft with no fuel, no engine, just a reflective surface pushed by ground-based lasers would not be subject to the Tsiolkovsky equation during acceleration. We will explore those concepts in detail later and discover why they fail for different but equally fatal reasons related to the same fundamental problem. For now, understand this fundamental truth that will anchor everything that follows in our exploration. If your spacecraft must carry the energy source that propels it, the rocket equation applies. If the rocket equation applies, exponential fuel mass growth governs your mission. And exponential fuel mass growth says that interstellar velocities require fuel masses that exceed any physical object humanity could ever construct. The distance to Proxima b is not actually the problem. Distance is just a number, a quantity of empty space to traverse. Given enough time, Even slow spacecraft could eventually cross that gulf. Time is not fundamentally the problem either. Humans could theoretically survive multi-generational journeys if the social and biological challenges were somehow solved. The problem is mass. Specifically, the problem is the exponential relationship between desired velocity and required fuel mass that emerges inevitably from momentum conservation. This exponential tyranny defines the boundary of human expansion into the cosmos. Everything that follows in our exploration will circle back to this central truth. Every clever engineering solution humanity has proposed runs into this wall. Every exotic propulsion concept crashes against this barrier. Every creative workaround fails against these mathematics. But perhaps better engines can push that wall back far enough to matter for some mission profile. Perhaps exhaust velocities orders of magnitude higher than chemical rockets can tame the exponential beast sufficiently for extremely minimal payloads or extraordinarily long journey times. Perhaps some propulsion concept exists that we have not yet fully analyzed. Our next chapter explores the most promising propulsion technologies ever conceived by physicists and engineers. We will calculate exactly what each one offers, and we will calculate exactly where each one fails against the immutable mathematics of the rocket equation. The numbers will show that even the most advanced theoretical concepts cannot rescue human interstellar travel from the tyranny of exponential mass growth. Rocket scientists have spent over a century trying to defeat the tyranny of the rocket equation. Generation after generation of brilliant engineers have devoted entire careers to pushing past the limits that mathematics imposes on spacecraft velocity. Their efforts produced remarkable technologies: nuclear engines that actually worked, plasma thrusters now flying on operational spacecraft, and theoretical drives that sound like they belong in science fiction rather than physics journals. Each technology promises higher exhaust velocities than its predecessors. Each technology genuinely moves the mathematical wall farther away from Earth. None of them tear that wall down. The quest for better propulsion resembles a prisoner digging through a cell wall with a spoon. Progress occurs. The wall recedes millimeter by millimeter, but the wall extends deeper than any spoon can reach, and the prisoner will die of old age before breaking through. This is not pessimism. This is mathematics. This is the fundamental nature of exponential functions applied to physical constraints that no engineering talent can overcome. Let us examine every serious propulsion concept ever proposed for interstellar travel. We will calculate exactly where each technology begins to fail, and precisely why the exponential function defeats every approach that requires carrying fuel. By the end of this analysis, you will understand that the problem is not insufficient funding, or inadequate engineering talent, or lack of political will. The problem is built into the structure of physical law itself. The problem exists because momentum must be conserved, and conserving momentum while accelerating mass requires expending mass. Chemical rockets established humanity's foothold in space. Every crewed mission that has ever flown, every Mars rover currently exploring the Red Planet, every probe sailing through the outer solar system launched using controlled chemical explosions. Liquid hydrogen and liquid oxygen combining in combustion chambers produce exhaust velocities around 4.5 kilometers per second. This represents the maximum energy density achievable through the breaking and forming of chemical bonds between atoms. We already calculated the futility of chemical propulsion for interstellar missions in our previous examination. Mass ratios climbing into numbers, exceeding atoms in the observable universe, become necessary for meaningful interstellar velocities. The fuel required to reach even modest percentages of light speed would exceed the mass of everything humanity has ever built. Everything on Earth, everything in the solar system. But chemical rockets establish the baseline against which all advanced propulsion technologies must be measured. They represent the starting point from which we climb toward better solutions, only to find that better solutions still fail against the same exponential wall. Nuclear thermal propulsion represents the first serious improvement over chemical rockets. The concept is elegantly simple in its fundamentals. Instead of burning hydrogen and oxygen together in a combustion reaction, you heat hydrogen propellant by passing it through the core of a nuclear fission reactor. The reactor runs incredibly hot, far hotter than any chemical flame can achieve. That intense heat expands the hydrogen gas and accelerates it through a rocket nozzle at velocities that chemical reactions simply cannot match, regardless of what fuel combinations engineers devise. The theoretical exhaust velocity for nuclear thermal propulsion reaches approximately 9 kilometers per second, more than double the 4.5 kilometers per second that chemical rockets achieve. This improvement sounds dramatic when first encountered. Doubling efficiency should halve the fuel requirement. A rocket that needs half as much fuel should be able to go twice as far or twice as fast. But the rocket equation does not work that way. The logarithmic relationship between exhaust, velocity, and mass ratio means that doubling exhaust velocity at low velocities helps enormously. But at the velocities needed for interstellar travel, doubling barely registers against the exponential growth curve. The improvement is real, but insufficient by factors that defy human comprehension. NASA developed and ground-tested nuclear thermal engines during the NERVA program throughout the 1960s. These engines were not theoretical concepts sketched on whiteboards and argued about in academic journals. They were physical hardware that engineers built with their hands, fueled with actual nuclear material, and fired in test stands in the Nevada desert. The engines worked precisely as predicted. They achieved the thrust levels and exhaust velocities that physics said they should. NERVA represented a genuine technological triumph that proved nuclear thermal propulsion was achievable with 1960s engineering capability. The program ended not because the technology failed, but because political priorities shifted away from ambitious space exploration. The Vietnam War consumed federal budgets that might otherwise have funded continued development. Public enthusiasm for space exploration waned after the Apollo moon landings achieved their primary political objective of demonstrating American technological superiority. The partial test ban treaty raised concerns about nuclear testing that complicated continued engine development. NERVA was shelved despite being technically successful, a victim of circumstance rather than physics. Modern space agencies are now revisiting nuclear thermal propulsion for missions to Mars. NASA and the Defense Advanced Research Projects Agency have funded new nuclear thermal rocket development programs. The higher exhaust velocity means spacecraft can reach Mars faster while carrying more payload per kilogram of fuel expended. Journey times to the red planet could shrink from 7 months to approximately 3 months. For Mars missions, nuclear thermal propulsion offers genuine and meaningful benefits that justify continued investment. For Proxima b, nuclear thermal propulsion offers nothing meaningful whatsoever. To reach 10% of light speed using nuclear thermal propulsion, the mass ratio required exceeds any construction project humanity could undertake on a planetary surface or in orbital facilities. Consider what this means in concrete physical terms. A spacecraft intended to deliver 1,000 kilograms of payload to Proxima b at this velocity would need to launch from Earth with a mass exceeding the entire infrastructure of a major metropolitan area, not the buildings themselves represented as equivalent mass, but actual physical mass of propellant and structure that would need to be assembled, launched, and accelerated together. And this calculation assumes perfect efficiency with no structural mass for fuel tanks, no reactor mass, no radiation shielding for crew or equipment. The actual mass would be far larger when realistic engineering enters the picture. Every kilogram of structure added to contain the fuel requires additional fuel to accelerate that structure. Every kilogram of reactor mass requires additional fuel. Every kilogram of radiation shielding requires additional fuel. The cascade compounds through the rocket equation until the numbers become not just impractical, but genuinely absurd, exceeding the mass of moons and planets. Nuclear thermal propulsion doubles efficiency compared to chemical rockets, but confronts the same exponential function that governs all propellant-based propulsion. Doubling the exhaust velocity does not halve the fuel requirement at interstellar speeds. The logarithmic nature of the rocket equation means improvements translate much more slowly than intuition suggests they should. Ion propulsion deserves careful examination because it represents the highest exhaust velocity technology that humanity has actually deployed on operational spacecraft flying real missions. Ion engines work by accelerating charged particles through electric fields, stripping electrons from propellant atoms, and then using electromagnetic forces to accelerate those ions to tremendous velocities. Operational ion engines achieve exhaust velocities between 20 and 50 kilometers per second. Some advanced designs under laboratory development push towards 70 kilometers per second. This exceeds chemical rockets by factors of 10 to 15. Surely such a dramatic improvement must help with interstellar travel. The mathematics crush this hope with the same cold indifference shown to every other propulsion technology. NASA's Dawn spacecraft used ion propulsion to tour the asteroid belt, visiting the giant asteroid Vesta and the dwarf planet Ceres with remarkable fuel efficiency that chemical rockets could never have matched. The ion engine operated for years, gradually accumulating velocity changes through patient continuous thrust. Dawn accomplished mission objectives that would have been impossible with chemical propulsion alone. For missions within the solar system requiring large total velocity changes over extended timeframes, ion propulsion offers genuine advantages that have been demonstrated in actual flight operations. But ion engines produce minuscule thrust despite their impressive exhaust velocities. The Dawn spacecraft's ion engine generated approximately 90 millinewtons of force, about the same pressure as a sheet of paper resting on your palm. Acceleration occurs over months and years, rather than the minutes or hours of chemical rocket burns. This patient accumulation of velocity works for missions to nearby asteroids where time constraints remain modest. It fails catastrophically for interstellar distances, where even modest velocities require thrust durations exceeding not just mission timelines, but human lifespans and civilizational continuity. More fundamentally, even 50 kilometers per second exhaust velocity cannot tame the exponential function at interstellar scales. To reach 5% of light speed using ion propulsion, approximately 15,000 kilometers per second, the required change in velocity divided by exhaust velocity yields a number around 300. The mass ratio equals e raised to that power. This produces a number so astronomically large that it exceeds comprehension entirely. We are not talking about billions or trillions. We are talking about numbers that dwarf the count of atoms in galaxies. The improvement over chemical rockets is real and substantial and completely irrelevant to the interstellar problem. Let me present the mass ratio progression across velocity thresholds to illustrate exactly how the exponential function operates and why no improvement in exhaust velocity can ever defeat it at sufficient scales. At 100 kilometers per second, roughly 6 times Voyager's record-setting velocity, ion propulsion requires mass ratios around 7 to 1. Every kilogram of payload needs 7 kilograms of propellant. At 500 kilometers per second, beginning to approach velocities that would reduce interstellar transit times from millennia to mere centuries, mass ratios climb dramatically. The natural logarithm of the mass ratio equals 10, meaning the actual ratio is e raised to the 10th power, approximately 22,000 to 1. Every kilogram of payload needs 22,000 kilograms of propellant. Still technically a number that can be written, but now exceeding any practical construction capability. At 1,000 kilometers per second, still only 1/3 of 1% of light speed, and still requiring over 1,000 years to reach Proxima b, the mathematics become truly brutal. The logarithm reaches 20, and the mass ratio climbs to nearly 500 million to 1. We have crossed into territory where the propellant mass exceeds planetary scales for any meaningful payload. At 3,000 kilometers per second, a full 1% of light speed, the logarithm reaches 60, and the mass ratio becomes e raised to the 60th power. This number contains 26 digits. It exceeds anything that can be meaningfully compared to physical objects in the universe. Scientific notation itself becomes merely a way to avoid writing strings of zeros that would fill pages. The exponential curve rises with terrifying steepness that human intuition completely fails to grasp. The function accelerates upward faster than any linear improvement in exhaust velocity can compensate for, no matter how dramatic that improvement might be. This mathematical reality explains why every propulsion technology we examine fails at essentially the same point in the analysis. The specific exhaust velocity determines where on the exponential curve the technology operates. At what velocity the mass ratio first becomes impractical and then impossible. Higher exhaust velocities shift the failure point to higher velocities. But the failure point always exists somewhere along the curve. The exponential function guarantees that sufficiently high velocities will always defeat any finite improvement in propulsion efficiency. Nuclear pulse propulsion takes a far more dramatic approach than any technology we have examined so far. Project Orion, studied extensively in the late 1950s and throughout the 1960s, proposed detonating nuclear bombs behind a spacecraft. Each explosion would push against a massive shock absorber plate mounted at the vessel's rear, accelerating the vehicle in discrete pulses rather than continuous thrust. The concept sounds insane at first description. Ride. Atomic explosions to the stars. Use weapons of mass destruction as propulsion. But the physics actually work, and the engineering was studied by some of the finest minds of a generation. A massive steel pusher plate at the rear of the spacecraft absorbs the impulse from each detonation. Shock absorbers mounted between the plate and the crew compartment dampen the acceleration to survivable levels for both humans and equipment. The explosions occur in rapid sequence, each one adding velocity. The spacecraft accelerates in dramatic pulses, rather than the smooth, continuous thrust of conventional rockets. But acceleration occurs nonetheless, and at rates far exceeding any chemical or nuclear thermal system. The genius of nuclear pulse propulsion lies in its ability to tap energy sources far beyond anything chemical or even nuclear thermal rockets can access through controlled reactions. A nuclear explosion converts a small percentage of mass directly to energy, according to Einstein's famous equation relating mass and energy. This energy release accelerates debris from the bomb to tremendous velocities. When that debris impacts the pusher plate, momentum transfers to the spacecraft. The exhaust velocity, effectively the velocity of bomb debris, far exceeds what any contained reactor can achieve. Theoretical exhaust velocities for optimized nuclear pulse propulsion reach 20 to 30 kilometers per second. Some designs using thermonuclear fusion bombs rather than fission devices pushed theoretical velocities higher still. Project Orion engineers calculated that properly designed nuclear pulse spacecraft could reach Mars in 4 weeks rather than 7 months. Missions to Jupiter would take roughly a year rather than a decade. The outer planets, the realm of ice giants and frozen moons that no human has ever approached, suddenly became accessible for crewed exploration within reasonable mission timeframes. Freeman Dyson, one of the 20th century's most brilliant and wide-ranging physicists, worked extensively on Project Orion during its active development phase. He calculated that a large Orion vehicle could potentially reach Alpha Centauri, the stellar system containing Proxima b, in roughly 130 years. This would require a spacecraft massing thousands of tons at departure, powered by hundreds of thousands of nuclear bombs detonated in sequence over years of acceleration, carrying a crew large enough to span multiple human generations during the journey. The engineering was audacious but not physically impossible. 130 years to reach another star. Multiple human generations living and dying aboard a vessel crossing the interstellar void. Children born knowing nothing but the interior of a spacecraft, raising their own children who would raise children who might finally arrive at the destination. The social and psychological challenges of such a mission boggle imagination and exceed any organizational feat humanity has ever attempted. But the physics permitted the journey at velocities around 3% of light speed. What if we demanded faster transit? What if mission designers wanted to arrive within a single human lifetime, rather than spanning generations? Transit times of 50 years rather than 130 would allow original crew members to potentially survive the journey if they departed young enough. This would maintain cultural continuity between departure and arrival. It would transform the mission from civilizational exile into something resembling actual exploration. 50 years to Proxima b requires approximately 8% of light speed, rather than the 3% that yields 130-year journeys. This seemingly modest increase in velocity, less than tripling the cruise speed, transforms the mass ratio calculation catastrophically. The exponential function governing fuel requirements does not respond linearly to velocity increases. Increasing velocity does not proportionally increase the fuel requirement. It raises the requirement by a factor that grows exponentially with each increment of added speed. The curve steepens as velocity increases, punishing each additional kilometre per second more severely than the one before. At 8% of light speed, nuclear pulse propulsion mass ratios return to impossible territory. The fuel requirements exceed anything that could be assembled in Earth orbit or manufactured from asteroid resources over any conceivable time frame. The wall that seemed breachable at 3% velocity rises again at 8%, as insurmountable as it ever was for any previous technology. Nuclear pulse propulsion pushed the wall back significantly. It made century-scale interstellar missions theoretically possible for the first time in serious engineering analysis. But it did not eliminate the wall. The exponential function still governs mass ratios. The tyranny still applies with full force at sufficiently high velocities. Fusion propulsion represents the next theoretical leap beyond nuclear pulse concepts. Instead of fission reactions that split heavy atoms like uranium into lighter fragments, fusion combines light elements like hydrogen isotopes into helium. This is the process that powers the Sun and every other star visible in the night sky. Stars are fusion reactors of astronomical scale, and fusion releases approximately 3 to 4 times more energy per unit mass than fission. Theoretical exhaust velocities for fusion propulsion range from 50 km per second to several hundred kilometers per second, depending on specific design configurations. At 100 km per second exhaust velocity, mass ratios for reaching 10% of light speed improve, compared to lower exhaust velocity systems, but remain daunting. The natural logarithm of the required mass ratio equals 300, which means the actual mass ratio is e raised to the 300th power. This number vastly exceeds anything that could be written in conventional notation without resorting to towers of exponents. At 500 km per second exhaust velocity, representing the theoretical upper limit for fusion energy before transitioning to more exotic matter-antimatter reactions, the mathematics finally produce numbers that can be discussed without immediate absurdity. Reaching 10% of light speed requires a velocity change of 30,000 km per second, divided by exhaust velocity of 500. The natural logarithm of the mass ratio equals 60. Here is where careful attention to mathematics becomes crucial. The mass ratio is not 60. The natural logarithm of the mass ratio is 60. The actual mass ratio equals e raised to the 60th power. This number, approximately 10 to the 26th power, still vastly exceeds any construction project imaginable. It exceeds the number of grains of sand on Earth. It approaches the number of atoms in a human body multiplied by billions. The problem with fusion propulsion is twofold, and both problems prove fatal to interstellar ambitions. First, practical fusion propulsion does not exist as deployable technology. After 7 decades of intensive research and hundreds of billions of dollars invested across multiple countries, humanity still cannot sustain a controlled fusion reaction that produces more energy than it consumes for power generation. let alone harness fusion energy for spacecraft propulsion. ITER, the International Fusion Experiment under construction in France, might achieve net positive fusion power generation by the mid-2030s if current schedules hold and no further technical obstacles emerge. Applying that laboratory achievement to a working spacecraft propulsion system would require additional decades of development beyond the already delayed reactor milestones. Practical fusion propulsion lies at minimum 50 to 100 years in the future if it proves achievable at all. But assume fusion propulsion eventually works. Assume engineers somehow solve the plasma containment problems, the neutron bombardment, damage to reactor walls, the temperature management challenges, the fuel injection systems, all the myriad technical obstacles that have stymied fusion development for generations. Assume exhaust velocities reach the theoretical maximum around 500 kilometers per second. Grant every optimistic assumption about fusion technology. Even with perfect fusion propulsion, the mass ratio mathematics remain catastrophic for crewed interstellar missions, and these calculations assume only acceleration. They ignore what happens when the spacecraft must stop. A crewed interstellar spacecraft cannot consist solely of payload and fuel in abstract mass categories. It must include crew quarters sized for humans spending decades aboard, life support systems that recycle oxygen, carbon dioxide, water, and waste continuously for 50 years without catastrophic failure, food production or storage facilities sufficient for however many years the journey requires, radiation shielding thick enough to protect human tissue from cosmic rays and stellar radiation during years of exposure outside any planetary magnetic field. The fusion reactor itself, which must contain plasma at temperatures exceeding the core of the Sun while remaining operational and controllable for decades of continuous operation. Navigation sensors and communication systems capable of functioning across interstellar distances where the nearest repair facility lies trillions of kilometers away. Medical facilities to handle injuries and illnesses, with no possibility of evacuation or external assistance. Spare parts for every critical system, because nothing can be resupplied during the journey. A realistic crewed fusion starship would mass not 1,000 kilograms, but hundreds of thousands of kilograms before adding any fuel. The spacecraft structure, systems, and provisions alone might approach millions of kilograms for a vessel expected to support human life reliably for 5 decades of continuous operation in the most hostile environment imaginable. But the deeper problem with fusion propulsion emerges when you consider the complete mission profile rather than just the outbound acceleration phase. All our calculations so far assume a one-way trip where the spacecraft accelerates toward Proxima b and then continues at cruising velocity indefinitely. The spacecraft reaches 10% of light speed and maintains that velocity throughout the journey. When it arrives at the destination star system, it screams through at 30,000 kilometers per second without slowing. The encounter with Proxima b lasts hours at most, as the planet grows from a point to a disk and shrinks back to a point in the rearview sensors. Then the spacecraft continues into interstellar darkness forever, too fast to be captured by any star's gravity, dwindling into the void between stars to coast eternally. This accomplishes almost nothing useful for human exploration or colonization. A flyby at 10% of light speed provides at most a few hours of close observation before the target recedes forever. No landing, no orbital insertion, no extended study of the destination world. Just photographs taken in passing before eternal departure. Any meaningful mission requires deceleration at the destination. The spacecraft must slow from cruising velocity to orbital speeds, or at least approach velocities that permit extended observation. You cannot land on a world while traveling at a significant fraction of light speed. You cannot conduct detailed scientific observations while racing through a star system faster than any natural object moves. Deceleration is not optional for any mission profile that intends to accomplish useful objectives upon arrival. Here, the rocket equation delivers its cruelest and most inescapable blow. Deceleration requires thrust in the opposite direction from travel. The spacecraft must fire its engines forward, pushing against its own motion, bleeding velocity kilometre per second by kilometre per second until it slows to useful speeds. This thrust requires propellant. The deceleration propellant must be carried from Earth, along with everything else. Every kilogram of fuel you need at arrival for deceleration must first be boosted to full cruising velocity during the acceleration phase of the mission. Think carefully about what this means mathematically. If your mass ratio for acceleration produces a natural logarithm of 60, meaning the actual ratio is e to the 60th, then the deceleration fuel becomes payload during the acceleration phase. You must accelerate the deceleration fuel along with the spacecraft structure and systems and crew. The fuel you need to slow down requires fuel to speed up. The fuel to slow down the fuel you need to slow down requires even more fuel to speed up. For a simple one-way mission with deceleration at the destination, the mass ratios compound multiplicatively rather than additively. The exponents in the rocket equation add together when you chain mission phases. If acceleration requires a natural log of 60 and deceleration requires another natural log of 60, the total becomes 120. The mass ratio climbs to e raised to the 120th power. The numbers leave any realm of physical meaning entirely. For a round-trip mission where explorers eventually return to Earth, the mathematics become truly catastrophic. A round trip requires 4 distinct propulsion phases: acceleration from Earth to cruising velocity, deceleration at Proxima b to useful arrival speeds, acceleration away from Proxima b back toward cruising velocity for the return journey, deceleration back at Earth to allow the crew to actually come home. Each phase adds its exponent to the total. The final mass ratio becomes e raised to the 240th power or beyond. Even one-way missions with deceleration face mass ratios far beyond the optimistic single-phase calculations. Unless mission designers accept pure flybys where spacecraft race through destination systems without stopping, every serious interstellar mission must carry fuel for slowing down at arrival. The rocket equation applies in both directions of travel, for speeding up and for slowing down. You cannot escape its constraints by flying in only one direction. This brings us to antimatter, the most exotic propulsion concept that still rests on actual verified physics rather than pure speculation about unknown phenomena. When matter contacts antimatter, both annihilate completely in a release of pure energy according to Einstein's equation relating mass and energy. The conversion efficiency approaches 100%. 1 kilogram of matter combined with 1 kilogram of antimatter releases energy equivalent to approximately 43 megatons of TNT explosive yield. This exceeds the largest nuclear weapon ever detonated by roughly 50%. No chemical reaction, no fission reaction, no fusion reaction approaches this energy density per unit mass of fuel. Antimatter propulsion could theoretically achieve exhaust velocities approaching significant fractions of light speed itself. The gamma rays produced directly by matter-antimatter annihilation travel at light speed by definition. If those gamma rays could somehow be directed for thrust, or if the annihilation energy could efficiently heat a conventional propellant to extreme temperatures, exhaust velocities might reach tens of thousands of kilometers per second, rather than the hundreds of kilometers per second that fusion propulsion achieves. At these exhaust velocities, mass ratios for interstellar velocities finally become truly manageable, even accounting for deceleration requirements. A spacecraft might reach 10% of light speed and then decelerate to orbital velocities with total fuel masses only a few times the payload mass rather than astronomical multiples. The exponential beast appears tamed at last by the most energetic reaction physics permits. But antimatter propulsion faces practical obstacles that make fusion look trivially easy to achieve by comparison. First, antimatter does not exist naturally in useful quantities anywhere in the known universe. The Big Bang produced nearly equal amounts of matter and antimatter in the first moments of cosmic existence, but matter dominated by a tiny fraction, and all the primordial antimatter annihilated against matter, within the first seconds after the universe began. Every antimatter particle that would be used for propulsion must be manufactured artificially using particle accelerators that convert enormous amounts of energy into tiny quantities of antimatter through inefficient quantum processes. The current worldwide production rate of antimatter totals approximately 10 nanograms per year. All the particle accelerators on Earth operating continuously at maximum capacity produce roughly 10 billionths of a gram of antimatter annually. To fuel even a small interstellar spacecraft would require grams or kilograms of antimatter. At current production rates, accumulating one single gram of antimatter would take approximately 100 million years of continuous production. Accumulating 1 kilogram would require 100 billion years, roughly 7 times the current age of the entire universe since the Big Bang. Second, even if production rates could somehow be increased through massive investment in dedicated antimatter production facilities, antimatter cannot be stored using normal containers made of normal matter. Antimatter annihilates instantly and completely upon contact with any matter whatsoever. Storage requires magnetic confinement of antimatter ions suspended in perfect vacuum, held away from all container walls by precisely maintained electromagnetic fields. The longest any significant quantity of antimatter has been stored under laboratory conditions is roughly 17 minutes. A Starship mission requires reliable storage lasting decades. Third, even if storage problems were somehow completely solved through revolutionary breakthroughs in containment technology, the energy required to produce antimatter necessarily exceeds the energy you can recover by annihilating it. The laws of thermodynamics guarantee this fundamental inefficiency. You cannot create any form of stored energy using less input energy than the stored energy contains. Antimatter is not a fuel source. It is an energy storage medium, and an extremely inefficient one at that. Antimatter propulsion represents our current theoretical ceiling for what might be possible, while still carrying your own fuel aboard the spacecraft. Even at that absolute ceiling representing the most energetic reaction physics permits, the technology prerequisites remain centuries beyond current capabilities if they prove achievable at all. The engineering challenges of antimatter production at scale, long-term storage, and controlled release for propulsion make fusion reactor development look like straightforward plumbing by comparison. And this is where every fuel-carrying propulsion system converges on the same inescapable truth. No matter how efficient your engine becomes, the rocket equation applies. You can push the mathematical wall back by increasing exhaust velocity. You can shift the point where mass ratios become impossible to higher velocities, but you can never escape the fundamental exponential relationship between velocity and mass ratio. That relationship emerges directly from conservation of momentum, one of the most thoroughly verified principles in all of physics. Every kilogram of velocity requires kilograms of fuel. Those fuel kilograms require more fuel kilograms to accelerate. The fuel to carry the fuel requires fuel to carry the fuel to carry the fuel. The cascade never ends. It only becomes more or less severe depending on your exhaust velocity, but severe or mild, the exponential relationship persists unchanged. The most advanced propulsion concepts humanity can currently envision push the wall back far enough that extremely long missions with extremely minimal payloads might become theoretically feasible within physics, if not within practical engineering. A tiny probe massing a few kilograms, a handful of miniaturized scientific instruments, perhaps an artificial intelligence system capable of autonomous operation and observation, accelerated for decades by patient continuous thrust, cruising for centuries through the interstellar void, decelerating for additional decades as the destination star approaches, arriving 1,000 years after departure to send data back to descendants of the civilization that launched it. But human crews, generation ships carrying thousands of colonists across centuries, spacecraft massive enough to land on and meaningfully explore an alien world, the fuel requirements return to impossibility, regardless of what propulsion technology you assume. No engine yet conceived can reduce mass ratios to levels compatible with crude interstellar missions at velocities that produce transit times shorter than geological epochs. Perhaps then the solution lies elsewhere entirely. Perhaps spacecraft should not carry fuel at all. If external energy sources located in the solar system could push starships to interstellar velocities, the entire framework of the rocket equation might be circumvented. A spacecraft with no onboard fuel would have no mass ratio to calculate. The exponential tyranny would simply not apply to the acceleration phase of the mission. This idea has attracted serious scientific attention and significant funding from sources that understand both the physics and the stakes. Laser propulsion systems would beam concentrated energy from installations in the solar system to accelerate departing spacecraft. Light sails would catch that beam and ride it toward the stars like sailing ships catching trade winds on Earth's oceans. The approach genuinely avoids the rocket equation for acceleration. Physics permits it completely. Engineering challenges exist but appear solvable in principle with sufficient development. But a new problem emerges when these externally propelled spacecraft approach their destinations. Problem that sounds completely different from the rocket equation, but leads inexorably back to the same mathematical wall. The problem of how to stop when you arrive, with the laser array that pushed you sitting 4 light-years behind you, and no way to slow down except the fuel you carried all along. Imagine a spacecraft carrying no engine, no fuel tanks, no propellant of any kind. Just an enormous mirror, thinner than a human hair, stretched across kilometers of space, its surface so reflective that it bounces back nearly every photon that strikes it. From Earth, the most powerful laser array ever constructed pumps trillions of watts of coherent light toward that distant mirror. Each photon that bounces off the sail transfers a tiny amount of momentum. Trillions of photons per second create measurable force. The spacecraft accelerates. No exhaust velocity governs this propulsion. No fuel mass sits aboard waiting to be expelled. The energy comes from home, beamed across the void at light speed, pushing the sail faster and faster. The Tsiolkovsky rocket equation, that mathematical tyrant that crushed every propulsion concept we examined, simply does not apply to a vehicle carrying no propellant. The tyranny appears to be defeated through elegant physics rather than brute force engineering. This concept has attracted serious scientific attention and substantial funding from people who understand both the physics and the stakes. The Breakthrough Starshot initiative launched in 2016 with $100 million in initial funding from Russian billionaire Yuri Milner. The project assembled an advisory board including the late Stephen Hawking, one of the most celebrated physicists of our era. Their goal seems modest compared to crude interstellar travel. Send gram-scale probes to Proxima Centauri at 20% of light speed. Arrival in roughly 20 years rather than millennia. Photographs and scientific data, returning to Earth within a human lifetime. The physics genuinely permit this approach for acceleration. Light carries momentum despite having no mass. When a photon reflects off a surface, it transfers twice its momentum to that surface. A sufficiently powerful laser array pushing against a sufficiently reflective sail can accelerate even substantial masses to interstellar velocities without violating any known physical law. The engineering challenges are immense but appear solvable in principle. 100 gigawatts of laser power focused on a 4-meter sail could accelerate a 1-gram spacecraft to 20% of light speed within approximately 10 minutes. The probe would experience acceleration forces exceeding 50,000 times Earth's gravity, but a solid-state wafer containing cameras and communication equipment could potentially survive such stresses. Scale the sail larger, and the acceleration period extends, but the underlying principle remains sound regardless of scale. Breakthrough Starshot represents humanity's most realistic near-term path to interstellar space. Tiny probes moving faster than any previous spacecraft, reaching the Alpha Centauri system, which contains Proxima b, within a single human lifetime. Transmitting photographs of an alien world back to the scientists who launched the mission. The people who push the button to fire the lasers might live to see images from another star. The project has made genuine progress. Engineers have fabricated prototype sails from materials thin enough and reflective enough to function as designed. Laser physicists have outlined pathways to the required power levels using phased arrays of thousands of smaller lasers working in precise synchronization. The technical roadblocks, while formidable, have defined solutions that require scaling existing technologies rather than inventing impossible new ones. For gram-scale probes conducting flyby observations, laser propulsion works. The physics check out. The engineering appears achievable within decades rather than centuries, but breakthrough starshot is not human travel to Proxima b. Gram-scale probes carrying cameras and communication chips cannot transport people. They cannot carry life support systems or food or water or radiation shielding. They cannot land on a planetary surface or establish a colony or conduct the kind of extended exploration that makes interstellar travel meaningful for human civilization. They are scientific instruments, remarkable and valuable, but fundamentally different from crude spacecraft. Scaling laser propulsion from gram-scale probes to human-carrying vessels reintroduces problems we thought we had escaped. The tyranny we circumvented through clever physics returns through the back door, wearing different clothes but carrying the same mathematical weapons. Consider what happens when we try to apply laser propulsion to crude interstellar spacecraft. A crude spacecraft must support human life for the duration of transit. Even under the most optimistic assumptions about mission duration, humans require certain minimum accommodations: pressurized crew quarters with enough volume to prevent psychological deterioration over years of confinement, life support systems that recycle oxygen, remove carbon dioxide, purify water, and process waste continuously without failure. Radiation shielding thick enough to protect human tissue from the cosmic ray bombardment that intensifies outside Earth's magnetic field. Structural integrity to survive decades of operation in the harsh environment of deep space. Minimum estimates for a crew of 6 spending 50 years in transit suggest a spacecraft massing at least 100,000 kilograms. This assumes revolutionary advances in closed-loop life support technology, minimal redundancy in critical systems, and crew willing to accept conditions more cramped than any submarine or space station ever built. Realistic estimates for spacecraft, providing reasonable living conditions over multi-decade missions, push mass requirements into hundreds of thousands or millions of kilograms. Accelerating 100,000 kilograms to 20% of light speed using laser propulsion requires power levels that dwarf any energy infrastructure humanity has ever constructed. The laser array would need to deliver not 100 gigawatts but petawatts, millions of billions of watts, sustained for extended periods. The sail would need to grow from 4 meters across to hundreds or thousands of kilometers across to intercept enough beam power for useful acceleration. The power requirements for a crude light sail exceed the entire current energy production of human civilization by factors of thousands. Every power plant on Earth, every nuclear reactor, every solar panel and wind turbine and hydroelectric dam would need to be multiplied many times over and dedicated entirely to pushing a single spacecraft. These challenges might theoretically be surmountable given centuries of development and solar system-wide industrial infrastructure. Orbital solar power stations, harvesting energy directly from the sun, vast laser arrays constructed from asteroid-mined materials. The combined industrial output of a civilization that has colonized the inner solar system. Perhaps, with enough time and resources, the power problem could be solved. But even granting unlimited power, even assuming humanity somehow builds a laser array capable of accelerating crude spacecraft to 20% of light speed, a problem emerges that no amount of Earthside infrastructure can address. The real barrier appears at the destination. Laser propulsion works by beaming energy from a stationary source to a moving spacecraft. The energy originates elsewhere. The propulsion system stays home. The spacecraft carries nothing but the sail and whatever payload hangs beneath it. When that spacecraft arrives at Proxima b traveling at 20% of light speed, 60,000 kilometers per second, it faces a challenge that the elegant physics of light sails cannot solve. The laser array sits 40 trillion kilometers behind it. Back in the solar system where the mission originated, light itself requires over 4 years to cross that distance. Even if the solar system lasers could somehow redirect and refocus to push against the sail in the opposite direction for deceleration, the spacecraft would overshoot Proxima b by trillions of kilometers before any braking beam could arrive. The mathematics here are unforgiving. At 20% of light speed, the spacecraft covers approximately 60,000 kilometers every second. During the 4 years required for any deceleration command to reach the spacecraft from Earth, the vessel travels roughly 7 trillion additional kilometers. By the time help could arrive from home, the spacecraft would be twice as far from Proxima b as Proxima b is from Earth. External propulsion systems cannot slow spacecraft down at distant destinations. The energy source remains stationary. The beam cannot follow the spacecraft indefinitely. Whatever arrives at the target star must provide its own deceleration capability. This requirement reintroduces the rocket equation with all its exponential consequences intact. Decelerating from 20% of light speed to orbital velocities requires velocity change comparable to the acceleration phase. You must shed 60,000 kilometers per second of speed to stop at your destination. If the spacecraft carries onboard propellant for this deceleration, the mass ratio mathematics return in full force. Every kilogram of deceleration fuel must be accelerated to 20% of light speed during departure. The fuel to slow down requires energy to speed up, using the most optimistic fusion propulsion with exhaust velocity around 500 kilometers per second. Decelerating from 20% of light speed to rest requires a mass ratio exceeding any number that retains physical meaning. The ratio climbs into ranges where scientific notation itself becomes cumbersome. The spacecraft would need to carry more fuel than exists in astronomical bodies. This is where the light sail's elegant escape from the rocket equation collapses. You can avoid the tyranny on the way out. You cannot avoid it when you need to stop. The mathematics simply wait at the destination, patient and implacable, demanding the same impossible fuel masses, whether you carried them from the start or hoped to avoid them through clever engineering. Perhaps deceleration requirements could be reduced through alternative approaches. What if the spacecraft did not need to stop completely? What if partial braking could achieve useful results? One proposal suggests using the destination star itself for deceleration. A magnetic sail, essentially a loop of superconducting wire generating a powerful magnetic field, could interact with the stellar wind from Proxima Centauri. Charged particles streaming outward from the star would push against the magnetic field, creating drag that gradually slows the spacecraft. Over years or decades of magnetic braking, the spacecraft might shed enough velocity to achieve capture into a bound orbit. The physics of magnetic sail deceleration remain uncertain. Theoretical studies suggest the approach might work under favorable conditions. Proxima Centauri produces stellar winds, though their intensity and consistency vary. A sufficiently large magnetic sail might extract meaningful braking from this stellar outflow, but magnetic sail deceleration introduces its own mass penalties. The superconducting wire loop must be substantial enough to generate fields capable of interacting with stellar wind at useful rates. The deployment mechanisms to unfurl such a structure after interstellar transit add mass. The cryogenic systems to keep superconductors at operational temperatures during the journey add more mass. Each kilogram added to the spacecraft must be accelerated by the departure laser, requiring proportionally more powerful ground-side infrastructure. More critically, magnetic sail deceleration operates slowly. The braking forces achievable through stellar wind interaction pale compared to rocket thrust. Instead of decelerating over hours or days like a conventional spacecraft, a magnetic sail might require years or decades to shed interstellar velocities. A spacecraft arriving at Proxima b at 20% of light speed might spend 50 additional years braking before achieving orbital velocities. This extended deceleration phase transforms mission timescales dramatically. Instead of arriving in 20 years as Breakthrough Starshot envisions, a crewed mission using light sail acceleration and magnetic braking might require 70 years or more for transit plus deceleration. The original crew would be elderly or deceased before the spacecraft achieved useful orbits around its destination. At such extended timescales, the advantages of high-velocity transit begin evaporating. If you must spend decades decelerating regardless, why accelerate to such extreme speeds in the first place? Slower departure velocities, with more conventional deceleration schemes, might produce comparable total mission durations with far simpler engineering. The magnetic braking concept reveals a fundamental tension embedded in interstellar travel physics. Fast transit times require high velocities. High velocities require either enormous onboard fuel supplies or external propulsion. External propulsion cannot follow you to provide braking. Any deceleration method adds either mass that must be accelerated at departure or time that extends the mission toward century scales. Every proposed solution either reintroduces the exponential fuel mass problem or extends timelines until the original advantages of the approach disappear. What about collecting fuel during the journey itself? If spacecraft could gather propellant from the interstellar medium rather than carrying everything from departure, the mass ratio problem might dissolve. The void between stars is not perfectly empty. Hydrogen atoms drift through interstellar space at densities averaging roughly 1 atom per cubic centimeter. A spacecraft traveling through this thin medium could theoretically scoop hydrogen for use as fusion fuel. This concept, called the Bussard ramjet, after physicist Robert Bussard, who proposed it in 1960, captured imaginations for decades. Science fiction embraced ramjets as the solution to interstellar travel, spacecraft that refueled continuously from the void itself, never running short of propellant, accelerating indefinitely toward the stars. The physics of interstellar ramjets present immediate problems that 60 years of analysis have failed to solve. First, the density of interstellar hydrogen is spectacularly low. 1 atom per cubic centimeter sounds like a measurable quantity until you calculate collection rates. A spacecraft traveling at 10% of light speed with a collection scoop 100 meters across would gather approximately 1 gram of hydrogen per day. This might sustain minimal thrust in an extremely efficient fusion reactor, but could never provide the propulsion rates needed for practical interstellar travel. Increasing collection rates requires increasing scoop size. Useful propulsion might demand collection areas measured in hundreds or thousands of square kilometers. The structural mass of such enormous scoops would exceed any reasonable spacecraft design. You would be accelerating more scoop than payload. Some proposals suggest electromagnetic scoops using magnetic fields to funnel charged particles toward the spacecraft without physical structures. Neutral hydrogen does not respond to magnetic fields. Ionizing the incoming hydrogen before collection requires energy expenditure that competes with energy gained from fusion. Second, the collected hydrogen presents a fundamental velocity problem. The atoms you scoop from interstellar space move at the same velocity as your spacecraft relative to your destination. From the spacecraft's reference frame, the hydrogen approaches from ahead at your travel velocity. To use this hydrogen in a fusion reactor, you must decelerate it relative to the spacecraft. The energy required to slow high-velocity incoming hydrogen approaches or exceeds the energy you could extract by fusing it. At interstellar velocities, the ramjet becomes an exercise in diminishing or negative returns. You spend more energy processing incoming fuel than you gain from burning it. The elegant concept of refueling from the void fails against thermodynamic reality. Third, even if collection somehow worked efficiently, the ramjet concept provides acceleration rather than deceleration. The fusion reaction expels propellant rearward, pushing the spacecraft forward. This helps you speed up. For deceleration, you would need to expel propellant forward relative to your motion. But incoming hydrogen approaches from ahead. After passing through any collection system, it emerges behind the spacecraft. The geometry works for acceleration only. Some theorists proposed reversing the ramjet for braking by somehow deflecting incoming particles to create drag. But the forces achievable through particle deflection at realistic interstellar densities remain far too weak for useful deceleration. The void is simply too empty to provide meaningful braking. The Bussard ramjet concept has been analysed exhaustively across 6 decades by physicists hoping to find configurations that work. No design produces net positive propulsion for practical interstellar missions. No configuration solves the deceleration problem. The idea fails against fundamental physics constraints that no engineering cleverness can circumvent. What if we positioned infrastructure along the route before the crewed mission departed? The depots would coast to predetermined positions along the interstellar trajectory. The crewed spacecraft would rendezvous with each depot in sequence, refueling without carrying all propellant from the start. The logistics of interstellar staging become absurd upon examination. A fuel depot must reach its designated position and then hold station there until the crewed spacecraft arrives. Getting the depot into position requires solving the same propulsion problems the crewed spacecraft faces. You need either external propulsion that cannot help with deceleration, or fuel-carrying propulsion subject to exponential mass ratios. Each depot confronts the identical tyranny. Each depot requires its own impossible fuel supply to reach and maintain position. The staging approach does not solve the mass problem. It multiplies it. Instead of one spacecraft needing impossible fuel quantities, you need dozens of depots, each requiring impossible fuel quantities. The total mass requirement exceeds the single spacecraft approach by the number of depots deployed. Perhaps the depots could be launched earlier using slow trajectories that minimize fuel requirements. Given decades or centuries of travel time, depots might coast to position using modest propulsion. But slow transit means the depots drift through space for extended periods before the crewed mission departs. Interstellar space offers no stable reference points. No gravity wells anchor objects in fixed locations. The depots would need station-keeping propulsion to maintain position over years or decades of waiting. This station-keeping requires fuel, which requires more depot mass, which requires more launch capability. The cascade continues, and the crewed spacecraft would still face the challenge of locating and rendezvousing with each depot at interstellar velocities. Navigation to reach a target hundreds of meters across after traveling trillions of kilometers presents enormous precision requirements. But the greater problem is velocity matching. If the spacecraft travels at 20% of light speed and the depot drifts through interstellar space, the spacecraft must decelerate to match depot velocity for any meaningful refueling. This deceleration requires the same fuel mass we were trying to avoid by staging. You cannot dock with anything while moving at 60,000 kilometers per second. Relative velocities during any rendezvous must drop to meters per second for safe approach. This velocity change from interstellar cruise speeds to docking speeds requires exactly the deceleration capability that staging was meant to avoid providing. Every staging architecture eventually requires the spacecraft to slow down. Slowing down requires onboard propellant. Onboard propellant means the rocket equation applies. The mathematics wait at every waypoint, undeterred by architectural complexity. This brings us to generation ships, the concept that seems to sidestep velocity requirements entirely by accepting extreme mission durations. If transit times measured in centuries become acceptable, spacecraft velocities can drop substantially. At 1% of light speed rather than 20%, a journey to Proxima b requires roughly 420 years. At 0.1% of light speed, the journey extends to 4,200 years. These velocities remain far beyond current capabilities, but demand less extreme propulsion than faster trajectories. Generation ships would carry not crews expecting to complete the journey themselves, but founding populations whose descendants would eventually arrive. Children born aboard would grow up knowing nothing but the ship's interior. They would raise their own children who would raise children who would raise children. After dozens of generations, descendants of the original crew might finally reach Proxima b and establish humanity's first foothold around another star. The concept has inspired science fiction for a century. Vast vessels containing thousands of colonists, self-sustaining ecosystems, recycling all resources indefinitely, societies evolving in isolation across centuries of travel, the romance of interstellar arcs carrying human civilization to distant shores. The physics and engineering reality devastates this romance completely. The generation ship must sustain a breeding population for centuries without resupply. Genetic diversity requirements suggest minimum populations around 500 individuals to avoid inbreeding depression over dozens of generations. Social stability considerations push estimates higher, perhaps into thousands of inhabitants. Each person requires not just survival but quality of life, sufficient to raise psychologically healthy children who will raise psychologically healthy children across unlimited generations. Food production must operate continuously without crop failure for hundreds of years. Life support systems must maintain atmospheric composition without accumulating toxins across centuries. Medical facilities must handle every conceivable health crisis, from birth complications to cancer to infectious disease outbreaks with no possibility of evacuation or external assistance. Mechanical systems must remain repairable, using only onboard resources and manufacturing capability. The ship must be a completely closed system, capable of autonomous operation longer than most civilizations in human history have persisted. Minimum mass estimates for such vessels reach into hundreds of millions of kilograms. Realistic estimates for ships providing reasonable living conditions across centuries climb into billions of kilograms. These masses require propulsion systems that scale accordingly. At 1% of light speed using nuclear pulse propulsion, mass ratios for generation ships return to impossible scales. The fuel requirements exceed the ship mass by factors that demand propellant quantities comparable to small moons, and these calculations assume acceleration only. Deceleration at the destination doubles the mathematical penalty. Round-trip capability, should descendants ever wish to return, compounds impossibility upon impossibility. Generation ships do not escape the rocket equation, they amplify it. Every additional crew member requires additional life support mass. Additional living space requires additional structural mass. Additional redundancy for century-scale reliability requires additional system mass. The generation ship concept attempts to trade velocity for time, accepting slower trips to reduce propulsion demands. But the mass penalty for sustainable human habitats overwhelms any benefit from reduced speed. You save fuel by going slower, but need more fuel to accelerate the vastly larger vessel required for extended habitation. This brings us back to the fundamental wall that every approach ultimately confronts. The rocket equation does not care about mission architecture. It does not distinguish between fast trips and slow trips, between small crews and large populations, between direct flights and staged approaches. It applies whenever spacecraft must change velocity using onboard propellant. Acceleration requires fuel. Deceleration requires fuel. Fuel has mass. Mass requires fuel to accelerate. This cascade governs every mission that travels anywhere and intends to stop. External propulsion avoids the cascade for acceleration only. The beam pushes you to speed. Then the beam stays home. When you need to slow down, you are alone with whatever mass you carried. And whatever mass you carried determines whether stopping is possible or impossible. No proposed concept escapes this fundamental constraint. Laser sails eliminate acceleration fuel, but cannot help with deceleration. Ramjets fail against interstellar medium density and thermodynamic limits. Staging multiplies the problem instead of dividing it. Generation ships amplify mass requirements instead of reducing them. every clever workaround leads back to the same mathematical wall. The rocket equation waits at the destination for any mission that intends to accomplish something useful upon arrival. Perhaps the solution lies in eliminating the most massive component of crewed spacecraft, the living crew themselves. What if humans did not need to remain conscious during transit? What if they could be frozen or suspended, reducing life support requirements to maintaining preserved bodies rather than active metabolisms? What if artificial intelligence systems operated the spacecraft while biological passengers slept through centuries? These concepts sound like they might finally defeat the tyranny. They do not. The final section explains why even eliminating human consciousness cannot solve the problem that mass imposes on interstellar ambitions. Cryogenic suspension appears in virtually every science fiction story involving interstellar travel. The concept feels intuitively correct as a solution to the impossible journey times that realistic physics imposes on spacecraft crossing between stars. Crew members enter specially designed pods where their biological processes halt or slow to near zero. Hearts stop beating. Neurons cease firing. Metabolism drops to levels indistinguishable from clinical death. Yet the body remains perfectly preserved, waiting for revival at some future moment when the destination star finally draws near. From the perspective of the suspended traveller, decades pass in dreamless instants. A century of transit feels like closing your eyes at departure and opening them at arrival with nothing in between. The appeal is visceral and immediate. If crew members do not experience the journey, the timeline becomes psychologically irrelevant. 100-year transit feels identical to a 10-year transit from inside the cryopod. The existential weight of watching years disappear, of knowing you will never see Earth again, of contemplating the deaths of everyone you ever knew while you drift through empty space. All of this unbearable psychological burden vanishes when consciousness itself is suspended. The journey becomes a discontinuity, a gap in experience, rather than an ordeal stretching across a significant fraction of a human lifespan. This psychological benefit has led many observers to assume that cryosleep solves the interstellar travel problem entirely. If humans can sleep through the centuries, surely spacecraft can take their time reaching distant stars. Slower velocities become perfectly acceptable when no one aboard experiences the passage of time. Mass ratios drop to manageable levels when you no longer need to reach high speeds. The tyranny of the rocket equation loosens its grip when patience becomes infinite. This reasoning contains a fundamental error that reveals itself immediately upon careful examination. Cryosleep solves the wrong problem entirely. It addresses human psychology while completely ignoring the physics that actually prevents interstellar travel. The crew is not the mass problem. Human bodies contribute negligible mass compared to the spacecraft systems required to transport them safely across interstellar distances. 6 crew members weigh perhaps 500 kilograms combined, less than a small car. The spacecraft systems supporting those crew members, keeping them alive, protecting them from radiation, maintaining their cryopods, providing for their eventual revival, weigh 100,000 kilograms at absolute minimum and likely far more. The ratio between crew mass and total spacecraft mass approaches 1 to 200. Adding or removing crew consciousness through suspension changes nothing meaningful about the fuel requirements that govern whether the mission is possible. Consider what a cryosleep-equipped interstellar spacecraft must actually carry, regardless of whether its passengers remain aware during transit or sleep through the centuries in frozen suspension. Life support systems must maintain atmospheric composition, temperature, and pressure around the cryopods throughout the journey, lasting decades or centuries. Even perfectly suspended humans require precise environmental control. The pods cannot simply be abandoned in vacuum at interstellar temperatures. Biochemical preservation of human tissue demands specific conditions maintained continuously for however long the journey requires. The equipment to provide this control weighs thousands of kilograms and requires power systems to operate without interruption across timescales exceeding any machine humanity has ever built for continuous operation. Radiation shielding must protect the suspended crew from cosmic rays and stellar radiation accumulated during decades or centuries of exposure outside any planetary magnetic field. The interstellar medium bathes everything, passing through it in high-energy particles that damage biological tissue at the cellular and genetic level. Without substantial shielding, accumulated radiation dose becomes lethal long before arrival, regardless of whether the crew is conscious to notice their own deterioration. Reducing this dose to survivable levels requires shielding mass measured in tens of thousands of kilograms. The shielding protects unconscious crew exactly as effectively as it would protect conscious crew. Suspension provides no defense whatsoever against particle radiation. Power systems must maintain cryopod function, spacecraft operations, navigation, and communication throughout journeys lasting decades or centuries. Nuclear reactors or radioisotope thermoelectric generators with operational lifespans exceeding anything humanity has ever constructed must operate reliably in the harsh environment of interstellar space. Redundant systems become essential because single points of failure become mission-ending catastrophes when the nearest repair facility lies trillions of kilometers distant. These power systems add thousands of additional kilograms that must be accelerated to cruising velocity regardless of crew consciousness state. Structural mass must contain all these systems and survive the mechanical stresses of acceleration and deceleration phases. A spacecraft cannot be flimsy when subjected to thrust forces over extended periods. Structural integrity against acceleration loads, micrometeorite impacts, thermal cycling, and decades of material stress requires substantial mass. That mass exists identically whether the crew sleeps or wakes during transit. Revival systems must awaken the crew upon arrival at the destination. Medical facilities must address complications arising from decades or centuries of suspended animation, a procedure no human has ever survived for more than hours in even the most optimistic laboratory experiments with the most favorable conditions. Diagnostic equipment, pharmaceutical supplies, surgical capabilities, rehabilitation systems for atrophied muscles and deconditioned cardiovascular systems must all be carried. The mass accumulates relentlessly with each system added. Survival equipment must support the crew after revival and throughout the operational mission phase. If the mission intends to explore or colonize Proxima b, landing craft and surface habitat equipment require transportation across interstellar distances. If the mission intends only orbital survey of the destination system, the crew still needs supplies for the observational phase that justifies the entire journey. Either way, substantial additional mass adds to the total. A realistic cryosleep-equipped spacecraft masses well over 100,000 kilograms before any fuel is loaded. The crew themselves contribute less than 1% of this total. Freezing them achieves nothing measurable against the fundamental mass problem. You could remove the crew entirely, replacing them with equivalent mass instrumentation, and the spacecraft would still mass 99% as much and face 99% of the same propulsion challenges. And that suspended crew still needs deceleration fuel at the destination. The spacecraft still must slow from cruising velocity to orbital speeds or approach velocities useful for the mission objectives. The rocket equation still governs this deceleration phase with full exponential force. The tyranny still rules regardless of whether the payload consists of conscious humans, suspended humans, robots, or pure instrumentation. Whether the payload breathes or not, it must still be decelerated, and deceleration requires propellant, and propellant has mass. Cryosleep accomplishes exactly one marginally useful thing in the context of interstellar mission planning. It eliminates the need for food production, exercise facilities, entertainment systems, and psychological support infrastructure during the transit phase. These mass savings might amount to 10 or 20% of total spacecraft mass, under optimistic assumptions about the relative mass of these systems. A 20% reduction in payload mass changes the required fuel mass by a similar fractional amount, but 20% reduction means nothing against exponential growth rates. If the original mass ratio was mathematically impossible, reducing it by 20% produces a slightly smaller mathematically impossible number. The mathematics remain absolutely fatal to mission feasibility. You cannot make infinity manageable by subtracting a finite amount from it. The genuine utility of cryosleep lies solely in extending psychologically acceptable journey times for the humans involved. If crew members experience no subjective duration during transit, then century-long journeys become personally acceptable in ways they never could be for conscious travelers watching decades disappear. A 25-year-old astronaut entering cryosleep could emerge at the destination still biologically 25 years old, while a century or more has passed in the external universe. From their personal perspective, they departed yesterday and arrived today. This psychological benefit permits mission planners to consider slower trajectories than conscious crew would tolerate. If timeline does not matter to the crew subjectively, perhaps spacecraft can travel at 1% of light speed rather than 10%. The velocity reduction improves mass ratios significantly because the exponential function punishes high velocities more severely than low velocities. But significantly better is not enough to transform impossibility into possibility. Even at 1% of light speed, requiring 424 years to reach Proxima b, deceleration fuel requirements remain exponentially impossible for any payload. Real mission requires. The wall moves farther away when you accept slower speeds. The wall does not disappear. It simply waits at a different velocity threshold. Cryosleep stretches acceptable timeline without solving the underlying physics. It makes the impossible journey feel shorter for the participants without making the journey actually possible. What about eliminating human presence entirely? Artificial intelligence systems could theoretically operate spacecraft indefinitely, without any biological vulnerabilities or support requirements. Robot explorers could reach Proxima b, study the planet in whatever detail their instruments permit, and transmit findings back to Earth across the 4-year light-speed communication delay. No life support systems consuming mass and power. No radiation shielding for fragile biological tissue. No food, water, or psychological needs. No timeline constraints imposed by human mortality or patience. This approach might actually work for limited mission objectives involving flyby reconnaissance or brief orbital surveys. But it is not human travel to Proxima b. The original question asks how long it would take humans to reach that distant world. Answering that robots could make the journey successfully while humans cannot does not resolve the question posed. It changes the subject to a different and less interesting question. Robot exploration of Proxima b would represent a valuable scientific achievement worthy of celebration. It would not constitute human interstellar travel in any meaningful sense. The distinction matters both philosophically and practically. Robotic probes extend human senses across cosmic distances, but they do not extend human presence or human experience. Data returning from Proxima b would inform human understanding of that distant world without providing any human the direct experience of being there. No person would feel alien gravity beneath their feet. No person would breathe alien atmosphere or fail to breathe it. No person would look up at an alien sky and see unfamiliar stars in unfamiliar patterns. The robots would go as our instruments. The humans would stay home as our species. This represents a fundamentally different relationship between humanity and the cosmos than actual human travel would provide. And even robotic missions face severe practical constraints upon detailed examination. A functional artificial intelligence system capable of operating a spacecraft autonomously across interstellar distances, making navigation decisions without ground control, input across communication delays measured in years, conducting meaningful scientific research, and transmitting useful findings across trillions of kilometers requires substantial physical infrastructure, radiation-hardened processors capable of surviving decades of cosmic ray bombardment without accumulating errors that degrade function, redundant computational systems because any critical single-point failure permanently ends the mission with no possibility of repair or recovery. Power supplies, with century-scale lifespans that have never been demonstrated in any space mission. Communication equipment capable of transmitting detectable signals across interstellar distances using antenna systems that must survive the journey intact. The mass accumulates even without biological passengers requiring life support. A minimal robotic probe stripped to absolute essentials might mass a few kilograms while retaining meaningful scientific capability. Breakthrough Starshot's target mass of 1 gram represents an extreme lower bound that sacrifices almost all functionality for mass reduction, carrying essentially nothing but a camera and minimal communication capability. At these minimal scales, laser propulsion becomes feasible for acceleration, as we discussed in examining external propulsion concepts. But deceleration returns as the limiting factor regardless of payload type or mission objective. A gram-scale probe cannot carry any meaningful deceleration capability whatsoever. It will fly through the Proxima Centauri system at 20% of light speed, snapping photographs for a few hours as the target world grows from a point of light to a disk and shrinks back to a point receding forever. Then the probe continues into interstellar darkness for eternity, its mission complete in the most minimal sense possible. This provides some data, certainly. It does not constitute exploration in any meaningful sense of the word. You cannot study planetary geology from a platform screaming past at 60,000 kilometers per second. You cannot search for biosignatures in atmosphere or surface chemistry with instruments operating for mere hours. You cannot map surface features in detail or measure atmospheric composition across seasonal cycles. The flyby probe takes snapshots and then vanishes. It glimpses rather than explores. Larger robotic missions capable of orbital insertion, extended observation, or actual landing face the identical mass ratio problems that crewed spacecraft face. Deceleration fuel requirements grow exponentially, regardless of whether the payload contains conscious humans, suspended humans, artificial intelligences, or scientific instruments. The rocket equation does not inquire about payload purpose or consciousness state. It governs momentum exchange. Mass is mass. Velocity is velocity. The mathematics apply with complete universality. Generation ships attempt to sidestep the velocity problem entirely by accepting extreme mission durations that would be psychologically intolerable for individual humans. If transit times measured in centuries become acceptable by design, spacecraft velocities can drop substantially from the levels needed for single lifetime journeys. At 1% of light speed rather than 10%, a journey to Proxima b requires roughly 420 years instead of 40 years. At 0.1% of light speed, the journey extends to 4,200 years. Generation ships would carry not crews expecting to survive the journey themselves, but founding populations whose distant descendants would eventually arrive at the destination. Children would be born aboard the vessel, knowing nothing but its interior as their entire world. They would grow up, receive education appropriate to the mission, form relationships, have children of their own, grow old, and die. Their children would repeat the cycle. Generation after generation would pass. Dozens of complete human lifetimes, while the ship crawled slowly toward Proxima b at velocities that seem modest only by comparison to light speed. After centuries of travel, descendants of the original crew, people who shared genes but nothing else with those who departed Earth, would finally arrive and perhaps establish humanity's first foothold around another star. The concept has inspired science fiction for over a century. Vast vessels containing thousands of colonists living complete lives in transit. Self-sustaining ecosystems, recycling all resources indefinitely. Societies evolving in isolation across hundreds of years of travel, developing their own cultures and traditions, and perhaps forgetting why they travel at all. The romance of interstellar arcs, carrying human civilization to distant shores, captures imagination like few other concepts. The physics and engineering reality devastates this romantic vision comprehensively and completely. A generation ship must sustain a breeding population for centuries, without any possibility of resupply from Earth. Genetic diversity requirements for a viable population, avoiding inbreeding depression over dozens of generations, suggest minimum starting populations around 500 individuals at absolute minimum. Social stability considerations, the need for diverse skills and roles and perspectives that healthy societies require, push practical estimates into thousands of inhabitants. Each person requires not merely survival, but quality of life sufficient to raise psychologically healthy children, who will themselves raise psychologically healthy children across unlimited generations, spanning the entire journey. Conservative estimates for minimal generation ships that might barely function suggest total masses exceeding 10 million kilograms. More realistic estimates for ships providing reasonable living conditions, psychological wellness, and long-term social stability climb rapidly into billions of kilograms, exceeding the mass of the largest structures humanity has ever constructed by enormous factors. The generation ship concept deserves deeper examination because its comprehensive failure illuminates exactly how the rocket equation compounds across every dimension of mission complexity. The failure mode is not simple. It is fractal, revealing new layers of impossibility at every scale of analysis. Consider what must function perfectly for a generation ship to succeed in its mission. Not function adequately, with occasional problems that clever crews can work around. Not function with regular maintenance and periodic repairs using onboard resources. Function perfectly, without catastrophic failure, across timescales exceeding the lifespan of every human institution that has ever existed in recorded history. The life support system must recycle atmosphere without accumulating toxic trace gases for 500 years of continuous operation. Carbon dioxide scrubbing must work every single day. Oxygen regeneration must proceed without interruption. Nitrogen balance must remain stable. Humidity must stay within acceptable bounds. Every chemical process involved must remain stable across 20 complete human generations. A 1% annual degradation in system efficiency, a rate so small it would be nearly undetectable in any single year of operation, compounds mathematically to total system failure within a century. The engineering tolerances required for multi-century operation exceed anything humanity has ever achieved for any system of any complexity in any environment. Food production must yield adequate nutrition for a population of thousands without crop failures across centuries of continuous operation. Agricultural systems on Earth, with all the advantages of planetary ecosystems, natural sunlight, and possibility of external assistance, regularly experience devastating failures from disease outbreaks, pest infestations, soil depletion, and environmental variation. A generation ship must prevent all such failures indefinitely, using only closed-loop systems with no possibility of external resupply. A single catastrophic harvest failure, the kind of event that occurs regularly in Earth agriculture, could doom the entire mission by starving the population. The redundancy required to prevent this outcome pushes agricultural system mass into ranges that compound devastatingly through the rocket equation. Medical facilities must handle every conceivable health crisis across dozens of generations of complete human lives. Genetic diseases will accumulate in a closed population despite careful breeding programs and genetic screening. Cancer rates will increase over baseline from cumulative cosmic radiation exposure, even with massive shielding. Infectious diseases will evolve in the closed environment, potentially in directions that overwhelm immune systems adapted to different conditions. Surgical capabilities, pharmaceutical production from raw materials, diagnostic equipment, specialized medical expertise, rehabilitation facilities, and mental health resources must all persist reliably across centuries. The mass of adequate medical infrastructure for a multi-century, multi-generation mission adds tens of thousands of kilograms at minimum. Social stability presents challenges that may exceed even the formidable technical difficulties. No human society in recorded history has ever maintained coherent purpose and functional organization across 500 years of continuous existence. Political systems transform or collapse. Religions evolve, schism, or fade into irrelevance. Languages drift until speakers separated by sufficient generations lose mutual comprehension. The crew who arrive at Proxima b after 5 centuries of transit would share almost nothing culturally, linguistically, or perhaps even conceptually with the crew who departed Earth. They might not even consider themselves bound by mission parameters established by ancestors they never knew and cannot meaningfully comprehend. Mutiny, civil war, religious schism, political fragmentation, or simple gradual loss of purpose could doom the mission long before propulsion physics intervened. Each of these failure modes requires additional mass to address through redundancy and backup systems. Redundant life support systems require mass. Backup agricultural facilities require mass. Comprehensive medical infrastructure requires mass. Architectural and social engineering to promote stability requires mass. The mass accumulates relentlessly with each identified risk, and every additional kilogram compounds through the rocket equation. But here is the truly devastating insight about generation ship concepts that transcends individual system failures. A generation ship is not simply a spacecraft with extra life support systems added on top of a conventional design. It is a spacecraft carrying fuel to accelerate life support systems that support people who consume resources that require production systems, that demand maintenance infrastructure that needs spare parts manufactured from raw materials, processed by industrial equipment, operated by trained personnel who themselves require life support systems that require resources that require production systems. Every system depends on every other system in complex webs of interdependency. The life support enables the crew who operate the industrial systems that produce the spare parts that maintain the life support. The food production enables the agricultural workers who maintain the food production. The medical facilities enable the medical staff who operate the medical facilities. The interdependencies create multiplicative rather than additive mass growth patterns. When you trace these dependencies through the rocket equation across every linked system, the final mass requirements exceed not merely moons or planets, but approach stellar masses for any reasonable cruise velocity that arrives within recorded historical timescales. The generation ship does not solve the interstellar problem. It demonstrates with devastating clarity how adding complexity to a fundamentally impossible baseline produces results that are exponentially more impossible rather than less. Now, apply the rocket equation to these enormous masses. At 10 million kilograms starting mass, representing the absolute minimum for a barely viable generation ship, even modest cruise velocities require fuel masses that strain imagination. At 1% of light speed using nuclear thermal propulsion, with exhaust velocities around 9 kilometers per second, the fuel requirements exceed the mass of large asteroids. The numbers climb rapidly toward planetary scales as you increase either ship mass or cruise velocity. With more advanced propulsion like fusion, mass ratios improve but remain staggering when applied to generation ship scales. A billion-kilogram vessel, more realistic for actual multi-century habitability, would require fuel supplies measured in tens of billions of kilograms, even with optimistic fusion propulsion assumptions. The logistics of assembling such fuel quantities in space exceed any industrial project humanity has ever contemplated. Generation ships multiply the mass problem by factors of thousands compared to minimal crewed missions. Every additional crew member adds mass. Every additional life support system adds mass. Every additional redundant system adds mass. The exponential function compounds each addition through the entire mission profile, amplifying already impossible numbers into realms of pure mathematical abstraction. The energy perspective illuminates the impossibility from a completely different analytical angle that nonetheless reinforces exactly the same conclusion. Consider the kinetic energy contained in a spacecraft massing 1 million kilograms traveling at 10% of light speed. This represents a modestly sized generation ship cruising at a modestly ambitious interstellar velocity. The kinetic energy stored in this moving object equals approximately 4.5 times 10 to the 20th joules, a number requiring scientific notation to express manageably. This number requires context to comprehend what it actually means. The total energy that human civilization currently produces from all sources combined, every nuclear plant and coal plant and natural gas plant and hydroelectric dam and solar panel and wind turbine and geothermal installation, every vehicle burning fuel and every factory consuming power, amounts to roughly 5 times 10 to the 20th joules per year of total output. The kinetic energy of our modest interstellar spacecraft at cruise velocity equals nearly 1 complete year of total human civilization energy production at current levels. But this calculation only accounts for the payload mass at final cruise velocity, ignoring everything required to reach that velocity. The fuel mass required to accelerate payload to cruise velocity far exceeds the payload mass itself, as we established in our examination of mass ratios. The propellant carries kinetic energy too during acceleration phases, and the efficiency of converting stored fuel energy into payload kinetic energy never approaches anywhere near 100%. Realistic mission energy requirements exceed the final payload kinetic energy by factors of tens or hundreds depending on propulsion technology and mission profile. A generation ship actually capable of reaching Proxima b at meaningful velocity would require total energy investments exceeding centuries of human civilization, energy production at current levels. Not years of total human energy output, centuries of total human energy output. The entire energy production of every human being and every human machine for multiple complete human lifespans would be insufficient to launch a single interstellar vessel with enough energy to reach another star. Some technological visionaries propose harvesting energy directly from the Sun using orbital megastructures called Dyson swarms, vast collections of solar collectors capturing stellar output before it radiates away uselessly into space. The Sun outputs approximately 3.8 times 10 to the 26th watts of power continuously. This vastly exceeds total human energy consumption by factors beyond meaningful comparison. Capturing even a tiny percentage of solar output would provide energy budgets exceeding anything civilization has ever contemplated. The mathematics confirm that stellar-scale energy harvesting could theoretically provide sufficient power for interstellar propulsion within physical law. The engineering required to construct such energy harvesting infrastructure lies centuries in the future at absolute minimum, if it proves achievable at all through any development pathway we can currently envision. Proposing Dyson swarms as solutions to interstellar travel does not actually solve the problem humanity faces. It defers the problem to hypothetical future civilizations whose capabilities we cannot predict or guarantee will ever exist. And even unlimited energy availability does not escape the rocket equation's exponential tyranny. Energy must be converted to momentum through propellant expenditure if you carry your own propulsion. The exponential mass relationship governs this conversion process, regardless of how much energy you have available to invest. Unlimited energy allows you to manufacture unlimited quantities of fuel. But manufacturing fuel does not eliminate the fundamental requirement to carry that fuel aboard the spacecraft and accelerate it along with everything else. The mass problem persists unchanged, even with stellar power sources at your disposal. The energy analysis thus confirms independently what the mass analysis already demonstrated through completely different reasoning. Interstellar travel at velocities producing human-relevant timescales requires resources so vast that no conceivable human project could provide them within any framework we can currently imagine. All paths lead to the same wall. Chemical propulsion cannot reach interstellar velocities under any circumstances. Fusion propulsion pushes it back further still. Antimatter propulsion pushes it back to the theoretical limit. But every propulsion system that carries its own fuel aboard faces the exponential barrier eventually. At some velocity threshold, depending on exhaust velocity, the required fuel mass exceeds any conceivable resource base. External propulsion elegantly avoids the acceleration problem, but cannot help with deceleration at the destination. The rocket equation waits patiently at arrival regardless of how cleverly you departed. Staging and in-flight refueling concepts multiply the problem rather than dividing it. Cryosleep and artificial intelligence eliminate psychological timeline constraints without addressing mass constraints whatsoever. The spacecraft still needs deceleration fuel. The fuel requirements remain exponentially impossible. Generation ships compound the mass problem by orders of magnitude rather than reducing it. More crew means more life support, means more infrastructure, means more structural. Mass means more fuel, means impossible numbers, piled upon impossible numbers. The Tsiolkovsky rocket equation is not a technological barrier, awaiting a clever engineering solution that sufficiently smart people will eventually discover. It is a fundamental mathematical description of how momentum conservation operates in a universe where spacecraft must carry their own propellant or somehow stop at destinations without external assistance. This physics cannot be circumvented through any known means. It can only be accepted as a constraint on what is possible. Some readers might wonder about truly exotic propulsion concepts that supposedly transcend conventional physics entirely. Wormholes connecting distant points through shortcuts outside normal space. Hyperspace, providing alternative travel pathways. These concepts appear in scientific literature, primarily as mathematical curiosities explored for theoretical interest, rather than engineering possibilities pursued for practical implementation. The Alcubierre warp drive requires negative energy densities to function, and negative energy has never been observed in any physical system under any conditions. Wormholes require stabilization using exotic matter with properties that contradict established physics. Hyperspace has no foundation whatsoever in any established physical theory. Invoking physics that might not exist to solve the interstellar travel problem is not a solution. We cannot plan actual missions around hypothetical physics that may prove impossible. We can only work with verified physical law, and verified physical law includes the rocket equation. If other intelligent beings exist around distant stars, they face exactly the same barrier we face. Their rocket equations function identically to ours. Their exponential mass growth follows identical mathematics. This shared cosmic confinement carries profound implications for the question of extraterrestrial intelligence and contact. Every technological civilization that might exist anywhere in the universe, around any star in any galaxy, confronts identical physics. Momentum conservation operates uniformly across all spacetime accessible to observation. The rocket equation applies equally to any species that must carry propellant. Exponential mass growth defeats any propulsion technology, regardless of how advanced the civilization that develops it becomes. If the universe contains 1 million technological civilizations scattered across 1 million galaxies, all million face the same wall. None can visit the others. None can send colonists to distant stars. None can build the galactic empires that populate human science fiction. Each civilization, no matter how ancient or technologically advanced, remains confined to its home stellar system by exactly the same mathematical barrier that confines us. The silence of the cosmos requires no conspiracy of alien civilizations deliberately hiding from our detection. It requires no zoo hypothesis keeping Earth quarantined from galactic society. The silence has a simpler explanation rooted in physics rather than speculative sociology. No one visits because no one can visit. The distances between stars do not prevent contact through some failure of ambition. The mass penalty for crossing those distances at useful speeds prevents contact through fundamental physical law. Every civilization that ever evolved or ever will evolve anywhere in the cosmos faces this identical barrier erected by momentum conservation itself. This transforms the question of extraterrestrial intelligence from a problem of detection into a problem of acceptance. We are not alone in facing cosmic isolation. Every thinking being anywhere in the universe shares our confinement within the same inescapable mathematics. There is strange comfort in this universality of limitation. Our inability to reach the stars is not a failure of human capability or human will or human cleverness. It is a feature of physical reality that applies everywhere and always to every form of intelligence, regardless of origin or development level. We did not fail to reach the stars through some inadequacy. The stars cannot be reached by anyone through any means consistent with verified physics. Human beings will not reach Proxima b. Not in 100 years. Not in 1,000 years. Not in 1,000,000 years. Not ever. Using any propulsion concept consistent with physical law as verified through observation. The distance is not the barrier. Given sufficient time, even slow spacecraft could eventually cross interstellar gulfs and arrive at distant destinations. The time is not the barrier. Cryogenic suspension or generation ships could theoretically survive multi-century or multi-millennium journeys if other physical factors permitted. The mass is the barrier. The exponential relationship between velocity and fuel mass creates resource requirements that no engineering can satisfy. At speeds relevant for interstellar travel within historical timescales, fuel masses exceed planets. At speeds that would accomplish anything meaningful within cosmic timescales, fuel masses exceed stars and galaxies and eventually the observable universe itself. This truth defines humanity's place in cosmic existence more starkly than any other fact physics has revealed. We developed intelligence and language and science and technology. We walked on our moon and sent robotic emissaries to neighboring planets. We have accomplished wonders that would have seemed miraculous to our ancestors, but the stars will remain points of light in our night sky forever. We can study them with ever more sophisticated instruments. We can perhaps send tiny probes for brief flyby observations. We can listen for radio signals from civilizations that might orbit them and wonder about minds we will never meet. We cannot actually travel there ourselves. Physics forbids it. The universe is not hostile to interstellar travel in any intentional sense. Hostility implies purpose, and the cosmos possesses no purpose. The universe simply operates according to physical laws that make interstellar travel impossible for beings who must carry propellant and decelerate at destinations. The rocket equation is not malicious. It merely describes how momentum conservation works across all physical systems. Proxima b orbits 25 trillion miles away. A world roughly Earth's size residing in the habitable zone of its parent star. A world that might harbour liquid water, alien atmospheres, perhaps even alien life adapted to the dim red light of a stellar ember. We have confirmed this world exists through careful observation. We can analyse its light and deduce some of its properties. We can imagine what walking on its surface might feel like, what its skies might look like, what sounds its winds might make. This world will never feel human footsteps. No astronaut will ever look up at Proxima Centauri's reddish glow from beneath an alien sky. No colonist will ever build a settlement on its ancient surface. No scientist will ever collect rock samples from its landscapes, or search for microbial life in its potential oceans. Imagination is all we will ever have of Proxima b. How long would it take humans to reach that distant world? The honest answer, the only answer consistent with verified physics, is that we cannot reach it at all. Not because we lack will or resources or cleverness, because physics itself forbids the journey through mathematics that cannot be argued with or engineered around. We are not stranded on Earth because the stars are far away. We are stranded because accelerating mass through space costs mass, and that cost grows exponentially with velocity. At the velocities needed to reach other stars within timescales that mean anything to mortal beings, the cost exceeds any payment the universe permits any civilization to make. The rocket equation ensures permanent confinement to our solar system for human beings, and likely for any biological intelligence anywhere. The mathematics cannot be disputed. The physics cannot be circumvented. The conclusion cannot be escaped through cleverness or determination, or hope. This is not a challenge awaiting a solution by smarter people in some future generation. This is a fact requiring acceptance by anyone who wishes to understand humanity's actual place in the cosmos. Human interstellar travel is impossible. The rocket equation proves it with mathematical certainty that no future discovery can overturn without overturning conservation of momentum itself. And conservation of momentum has never failed in any observation across the entire history of physics. The stars are beautiful. The stars are forever unreachable. These two facts coexist without contradiction, describing a universe that permits us to see wonders we can never touch. Perhaps this capacity for understanding represents humanity's true cosmic significance, despite our physical confinement. We are matter that knows it is trapped. We are minds that can grasp the dimensions of our cage. We are the universe becoming aware of its own structure, including the parts of that structure that permanently confine awareness to isolated islands scattered across an ocean that cannot be crossed. The stars will remain forever out of reach. And we will remain forever capable of contemplating what we cannot touch, finding meaning in understanding even when understanding reveals limitation.